There's something truly special about watching a log transform from a towering forest giant into precision-cut lumber. It's a process that connects us to centuries of American craftsmanship, yet relies on technology that would have seemed like pure science fiction to the Sawyers of yesteryear. Today, we're taking you inside Biewer Winona, Inc., a state-of-the-art sawmill operation nestled in Winona, Mississippi, where tradition meets innovation in the heart of America's timber country. Mississippi has always been lumber country. In fact, at the turn of the 20th century, Mississippi was the leading lumber-producing state in the entire nation. The old-timers used to say you could smell the pine sap in the air from miles away when the mills were running full tilt. While the massive virgin forests of that era are long gone, operations like Biewer Winona carry forward that proud heritage with sustainable forestry practices and cutting-edge technology that ensures this renewable resource will be here for generations to come. Let's start where every great piece of lumber begins, deep in the forest. The harvesting operation you're seeing isn't your grandfather's logging crew, though the fundamental goal remains the same. Modern timber harvesting is a carefully orchestrated dance of precision equipment and skilled operators. The feller buncher you're watching is essentially a massive mechanical hand that can grasp a tree, cut it at the base, and gently lay it down in a matter of seconds. These machines typically run on tracks, distributing their weight to minimize soil compaction and environmental impact. The operator sits in a climate-controlled cab with 360-degree visibility, using joystick controls that would feel right at home in a video game, except here, the stakes are considerably higher. What's fascinating about modern feller bunchers is how they've evolved. The first mechanical tree harvesters appeared in the 1950s and were crude, unwieldy beasts that broke down constantly. Today's machines are equipped with computer systems that can measure tree diameter, calculate optimal cutting angles, and even track production in real time. The cutting head typically features a chainsaw bar and chain that can slice through a 2-foot diameter pine in under 10 seconds. It's a far cry from the 2-man crosscut saws that logging crews relied on for centuries. Once the trees are felled, notice how they're processed right there in the woods. The delimber and slasher equipment strips away branches and cuts the trunk into optimal lengths for the mill. This is where the operator's experience really shines. They're making split-second decisions about how to maximize value from each log, considering factors like wood quality, defects, knots, and market demands. A skilled operator can boost the value of a load by 20% or more compared to someone just starting out. Now here's something that really showcases the evolution of the industry. See those log trucks being loaded? Modern logging operations use sophisticated load optimization software. The equipment operator isn't just stacking logs randomly, they're arranging them to maximize the load while maintaining proper weight distribution for safe highway transport. Those trucks can legally carry up to 80,000 pounds in most states, and every pound matters when you're running a profitable operation. The loading process itself has become an art form. The grapple skidder or loader carefully positions each log, often alternating large and small pieces to create a stable load that won't shift during transport. As these loads arrive at the Biewer Winona facility, they're entering what is essentially a carefully choreographed industrial ballet. The first stop is the log yard, which might look like organized chaos to the untrained eye, but is actually a precisely managed inventory system. Logs are sorted by species, diameter, length, and quality grade. Southern yellow pine, which is what you're primarily seeing here, has been the backbone of American construction for over a century. Its strength-to-weight ratio, natural resistance to decay, and straight grain make it ideal for everything from framing lumber to utility poles. Here's a bit of fascinating history for you. The system of grading and sorting lumber that we use today was largely standardized in the 1920s and 30s. Before that, every mill had its own grading system, which made commerce incredibly complicated. A number 1 common at one mill might be completely different from another mill's product with the same name. The standardization of lumber grades was one of those quiet innovations that transformed an entire industry and made modern construction as we know it possible. The debarking process you're watching now is the first major transformation the logs undergo. Those massive rotating drums with their carbide-tipped teeth strip away the bark in minutes. This serves multiple purposes. First, bark contains dirt, rocks, and grit that would quickly dull the expensive saw blades downstream. Second, the removed bark isn't wasted. Mills typically use it for landscaping mulch, boiler fuel, or sell it to paper mills. Nothing goes to waste in a modern sawmill. It's both environmentally responsible and economically smart. The old saying in the lumber business is, "We use everything but the squeal," borrowed from meatpacking, but it certainly applies here. After debarking, logs move to the scanning station. This is where technology really starts to shine. Modern sawmills use laser scanning systems, sometimes combined with X-ray or CT scanning technology, to create a three-dimensional map of each log. The computer analyzes this data in milliseconds, identifying the optimal cutting pattern to maximize yield and value. It accounts for taper, sweep, crook, and internal defects that might not be visible from the outside. This technology didn't exist when many of us were starting our careers. Back in the day, the head sawyer made these decisions based on experience and intuition, eyeballing each log and making judgment calls. They were remarkably good at it, but even the best human sawyer can't match the consistency and optimization of modern scanning systems. Now we're getting to the heart of the operation, the primary breakdown saw. What you're seeing is typically called a head rig or head saw. This is where the log makes its first pass through the mill. Modern head rigs can be band saws, circular saws, or, increasingly, thin kerf saws that waste less wood. The saw you're watching is likely making its cuts at speeds that would terrify the old-timers. The precision is incredible. These saws can hold tolerances of plus or minus 1/16 of an inch, while screaming through logs at highway speeds. The kerf, that's the sawdust produced by the blade's thickness, has been a focus of innovation for decades. Traditional circular saws might have a kerf of a 1/4 inch or more. Thin kerf technology has revolutionized mill efficiency. Some modern saws have kerfs as narrow as 1/8 of an inch. On a large log, reducing the kerf by just 1/8 of an inch can yield an extra board or two from each log. Multiply that by thousands of logs, and you're talking about serious money and better resource utilization. After the primary breakdown, the cant, that's the squared-off centerpiece, and the sideboards move to the gang saws or resaws. This is where things really get divided up into the familiar dimensions we see at the lumber yard: 2x4s, 2x6s, 2x8s, and so on. The edger saw then trims the rough edges off these pieces, creating clean, straight edges. Again, computer optimization is at work here, determining the best way to maximize the value from each piece, while meeting market demands. What's particularly interesting is how market conditions influence production decisions in real time. If 2x4s are commanding premium prices while 2x6s are soft, the mill can adjust its cutting patterns accordingly. This flexibility is a huge advantage of modern sawmilling. The old-style mills were much more rigid in their production capabilities. You cut what your equipment could cut, and hoped the market wanted it when you were done. The trimmer saw is another critical station. These are usually multiple blade saws that cut boards to precise lengths: 8 feet, 10 feet, 12 feet, 16 feet, and so on, while also removing defects from the ends. The speed and precision of these trimmers is really something to behold. They're making multiple cuts per second, each one optimized to maximize value and meet quality standards. Some defects, like knots or splits, can be cut out, turning one lower-grade longboard into 2 higher-grade shorter boards. This defecting process is where experienced lumber graders really earn their keep, even in highly automated mills. Now, here's something that connects us to the past. See those lumber graders examining the boards? The fundamentals of what they're doing haven't changed in a century. They're looking at knot size and placement, grain characteristics, moisture content, and a dozen other factors. Sure, some mills have automated grading systems using cameras and AI, but many still rely on trained human graders because lumber quality assessment requires a level of judgment that's hard to fully automate. These folks are the inheritors of a tradition that goes back to the earliest commercial sawmills. A good lumber grader in 1925 would feel right at home with the task, even if the equipment around them would seem like magic. The sorting and stacking process you're watching now is where organization becomes paramount. Lumber is sorted by dimension, length, and grade, then stacked in precise configurations. Those stacks aren't random. They're built with spacer strips, called stickers, placed between layers to allow air circulation. Proper stacking is crucial for the next phase, drying. Poorly stacked lumber will warp, twist, and be ruined. Most construction lumber today is kiln dried, though some operations still use air drying for certain products. Kiln drying is a carefully controlled process where lumber is placed in massive ovens and heated while humidity is precisely managed. A typical kiln schedule for southern yellow pine might take several days, slowly reducing the moisture content from around 50% or more in green lumber down to 19% or less for kiln-dried stock. This process requires real expertise. Dry the lumber too fast, and it splits and checks. Too slow, and you're wasting time and energy. Too much or too little humidity at various stages causes different problems. The kiln operators are following schedules developed over decades of experience in testing. Here's a bit of trivia that really shows how far we've come. In the early days of commercial lumber production, most lumber was sold green, right off the saw. Buildings were constructed with wood that was still full of moisture. As the lumber dried in place, it would shrink, warp, and twist, causing all sorts of problems. Doors that fit perfectly when installed would stick or gap a year later. Floors would develop cracks. It wasn't until the mid-20th century that kiln-dried lumber became the standard for construction. This single change dramatically improved building quality and reduced callbacks and complaints. The final stages of processing include planing, where the rough-sawn lumber is smoothed to final dimensions and given a clean surface finish. Those planers are essentially giant versions of a woodworker's hand plane, but operating at industrial scale and speed. The dimensional consistency achieved by these machines is remarkable. When you buy a 2x4 at the lumber yard, it's actually 1.5 by 3.5 inches. Those precise dimensions, consistent from one end of the country to the other, are possible because of the standardization and precision of modern planing equipment. What really strikes me about operations like Biewer Winona is how they've managed to maintain profitability and sustainability in an industry that's seen tremendous changes over the past few decades. The lumber industry has faced challenges from global competition, changing building codes, environmental regulations, and shifting market demands. Mills that have survived and thrived are the ones that have invested in technology, efficiency, and quality while maintaining the skilled workforce that makes it all work. The productivity differences between modern mills and those of even 30 or 40 years ago are staggering. A mill like this might process in a single shift what would have taken a week or more in the old days. Yet they're doing it with better resource utilization, higher quality standards, and safer working conditions. That's genuine progress. The Sawyers of the 1950s worked in conditions that would shock us today. The noise, the danger, the physical demands were all tremendous. Modern mills are still demanding places to work, make no mistake, but they're dramatically safer and more ergonomic than their predecessors. This brings us full circle to where we started in the forest. Sustainable forestry practices mean that well-managed timberlands produce more wood today than they did when they were first harvested. Trees are a renewable resource, but only if managed properly. For every tree harvested in well-managed forests, several are planted. Southern pine, being a relatively fast-growing species, can reach harvest size in 25 to 35 years under good conditions. Compare that to the old-growth forests that took hundreds of years to develop, and you can see why sustainable forestry is both possible and necessary. Operations like Biewer Winona depend on that renewable supply chain, which gives them every incentive to support good forestry practices. Now let's shift gears and look at a different kind of wood processing operation. Pixelle Specialty Solutions represents another chapter in the story of how we transform trees into products that shape our daily lives. While sawmills like Biewer turn logs into lumber, paper mills like Pixelle take wood and break it down to its most fundamental components before rebuilding it into something entirely different. It's a process that's both ancient and ultra-modern, combining chemistry, engineering, and physics in fascinating ways. Pixelle Specialty Solutions continues that tradition, but with a focus on high-quality specialty papers. These aren't your everyday office copy papers. We're talking about papers used for labels, flexible packaging, coated papers for high-end printing, and specialty industrial applications. Each type requires specific characteristics: strength, smoothness, absorbency, coating ability, and more. Achieving these properties starts with the wood that enters the facility. The logs arriving at Pixelle undergo a different destiny than those at a sawmill. Here, the goal isn't to preserve the wood's structure, but to deconstruct it completely. After debarking, similar to what we saw at Biewer, the logs move to the chipping operation. These industrial chippers are absolutely massive machines that reduce entire logs to chips the size of cornflakes in seconds. The chips need to be relatively uniform in size because consistency in the raw material leads to consistency in the final product. Here's where it gets really interesting from a chemistry standpoint. Those wood chips head to the digesters, which are essentially giant pressure cookers. In the kraft pulping process, the most common method for strong papers, chips are cooked with a mixture of sodium hydroxide and sodium sulfide at high temperature and pressure. This chemical cooking process dissolves the lignin, the natural glue that holds wood fibers together, while leaving the cellulose fibers largely intact. The kraft process was developed in Germany in the 1870s, and the name comes from the German word for strength. Before kraft pulping, most paper was made using mechanical pulping or older chemical processes that produced weaker paper. Kraft revolutionized papermaking because it could handle any species of wood and produce incredibly strong paper. Those old brown paper grocery bags? Classic kraft paper. And they could hold surprisingly heavy loads without tearing. After digesting, the pulp goes through washing to remove the spent cooking chemicals, which are recovered and reused. Then comes bleaching for products that need to be white or light-colored. Modern bleaching has evolved significantly. The old chlorine-based processes, while effective, had environmental concerns. Today's mills often use oxygen, ozone, and hydrogen peroxide-based bleaching sequences that are much more environmentally friendly while still achieving the brightness customers demand. The cleaned and bleached pulp is now ready for the paper machine, and this is where things get truly impressive. Modern paper machines are among the largest, most complex, and fastest production equipment in any industry. We're talking about machines that can be the length of a football field, operating continuously at speeds up to 60 miles per hour or more, producing paper that's uniform to within thousandths of an inch in thickness. The precision involved is extraordinary. The papermaking process starts with the pulp being diluted into a slurry that's more than 99% water. This watery mixture is spread onto a moving wire mesh screen, called the forming fabric. As the fabric moves at high speed, water drains through the mesh, and the fibers begin to interlock and form a mat. This is where the paper's basic structure forms. The orientation of fibers, their length, how they interlock, all of this affects the final paper's properties. Some papers need to be strong in one direction for printing press applications, while others need equal strength in all directions. As the paper web moves down the machine, it passes through a series of pressing sections where heavy rollers squeeze out more water while compressing the fibers together. The pressure applied here affects paper density and smoothness. Too much pressure makes paper too dense and less absorbent. Too little leaves it weak and fuzzy. Again, it's all about balance and knowing what properties your final product needs. Next comes the dryer section, which typically consists of dozens of heated cylinders. The paper web snakes back and forth across these steam-heated drums, and the moisture content drops from around 60% after pressing down to about 5% in the finished product. The temperature and humidity in the dryer section must be carefully controlled. Dry too fast, and the paper becomes brittle and prone to breaking. The web breaks on a modern paper machine are dramatic events that can take hours to clean up and restart. For many specialty papers, including those Pixelle produces, coating is a crucial step. Coating involves applying a layer of minerals, typically clay and calcium carbonate, mixed with adhesives and other chemicals. This coating layer is what gives many papers their smooth, bright printing surface. Finally, the paper passes through a calendaring stack, a series of heavy rollers that compress and smooth the surface to final specifications. Some papers go through soft nip calendars for a smoother finish without excessive compression, while others need the high pressure of traditional hard nip calendars. The finished paper is then wound into massive rolls that can weigh several tons each. These parent rolls will later be slit into smaller rolls sized for customers, printing presses, or converting equipment. What's remarkable about modern papermaking is the level of quality control involved. Throughout the process, sensors continuously monitor thickness, moisture content, brightness, strength, and dozens of other parameters. Computer systems make automatic adjustments to maintain specifications. Despite operating at highway speeds with a product that's initially 99% water, modern paper machines maintain tolerances that would have been impossible just a few decades ago. A typical quality specification might call for thickness variations of no more than 3% across the width of the sheet. Meeting that consistently at 3,000 feet per minute is genuinely impressive engineering. The paper industry has adapted to changing markets. While newsprint and office paper demand has declined in the digital age, specialty papers for packaging, labels, and technical applications have grown. Companies like Pixelle that focus on these higher-value specialty products have found success by being nimble and quality-focused.